In the previous video, we introduced the possible performance bottlenecks in a GPU. Starting from this video, we're going to look at the reasons that may block the performance of a GPU kernel. We start with the consideration of the block and the grid size decision. We're going to introduce an example that is called image gamma, which is a relatively compute-intensive workload. So let's look at this example. When we're taking a photo, the image may be too dark or too bright, so we want to adjust the brightness of the image. What can be the algorithm that can help us tune the brightness of this image? So let's look at the image and see how an image is represented in a memory. In memory, the image is organized in pixels. Within each pixel, there are three numbers. The first one is R, which represents the brightness of the red channel. And we have G and B, which stands for green and blue respectively. So for a brighter pixel, we have larger numbers. You see this RGB for this green cell is higher. And for this darker cell, we have a number that is smaller. Here we have 64, 37, and 17. These numbers here are represented in 8-bit unsigned integers, which ranges from 0 to 255. We can also represent the brightness in a floating point number from 0 to 1, where 1 represents the brightest value. Then we can use this equation, V out equals AV in gamma, to tune the brightness of the picture. Here, this A is a parameter we typically set it to 1, and this is gamma is something we can tune. Consider this V in and V out are numbers between 0 and 1. If this gamma is 1, then the output will equal to the input. If this gamma is 2, the number will actually become smaller and the image will become darker. As we can see from this series of pictures, we can see that the smaller gamma, the brighter of the image will be. Using this algorithm, we can tune the brightness of an image. From the previous videos, you may have no big problem writing this type of kernel. If we represented values of all the channels and all the pixels as a big array, we can consider this is an embarrassingly parallel workload. So the kernel can be written like this. We have an image gamma kernel. We have an unsigned int image. We have a gamma, which is a floating point number. And we have the number of pixels. Here, the number of pixels is actually 3 times the number of pixels because we consider 3 channels. Now, we first get the index of this array. Now, we do a boundary check. If the index is smaller than the number of pixels, we perform this operation. So you can see the D image index divided by 255 is converting the range from 0 to 1. Then we do the power operation. We multiply the number by 255 to convert it back to an unsigned int 8 value range. So this is the simplest implementation. And from our previous videos, you may also write this type of implementation. And here, our assumption is we have 1 thread per number, per pixel or per channel. Then the block size can be anything smaller than 1024. You can set it to 32, you can set it to 64, you can set it to 256, you can set it to 512. The execution result will be exactly the same. So you may wonder, what can be the block size that I set? If I set it to 1, can it get good performance? Or I set to 1024, can it get good performance? By the way, you cannot set a value that is greater than 1024 because the hardware capacity is 1024. So if you set it to 1024, you may get an error after launching the kernel. So I run this program on an MI50 GPU, and these are the values I get. And the x-axis is the block size, and the y-axis is the execution time in milliseconds. The smaller the number, the faster the execution. We can see here there's a jigsaw pattern. When we have 1 thread per block, the execution time is extremely long. This is because the GPU can execute 64 threads in parallel because each wavefront is 64 threads. But if you only utilize 1/64th of the computing power, we will have a lot of blocks, we'll have a lot of wavefronts, and it's a waste of computing resources. And as you can see, the performance improves as we approach to 64. If we set it to 65, the execution time will almost double there. because we have one extra thread that has nowhere to go, so it will occupy a new wavefront. In that case, we'll have two wavefronts per block. And then the second wavefront only have one thread within the 64 thread wavefront. And again, we waste almost half of the computing resources. As you can see, the bottom line is relative constant. That means if we set it to a multiple of 64, we get almost the same performance, which is slightly higher than 60 milliseconds. So the conclusion here is we always want full wavefront. We don't want partial wavefront. How we can get a full wavefront is to set the block size to a multiple of wavefront sizes. And by default, AMD GPUs has a wavefront of 64. So multiple 64s are the best options. Then the question is, can we do better than this? We want to reason about this process, the command processor and dispatch to each compute unit. So the command processor will dispatch one block to a compute unit, which may take some time. Then it will dispatch another block to another compute unit, which will take some other amount of time. Then eventually, we dispatch every block to all the compute unit, which takes some time. So this dispatching process creates overhead. So if we have very long running wavefronts, this dispatching time can be neglected. But in our image gamma example, or in vector add example, or in many embarrassingly parallel workload, we typically do a small amount of task. Then we retire the wavefront. In this case, the dispatching overhead cannot be neglected. So what's the solution? The solution is we want each wavefront to run a little bit more task. Then we have fewer blocks to dispatch. So in this case, we want to revise the implementation to make it more efficient. This is the original implementation. Let's move on to make it to perform more tasks. To perform more tasks means each thread can no longer only process one pixel, but it needs to process more pixels. So it's simple. We can convert this if statement to a for statement to make it into a loop. So here, we need to decide how we can partition the workload. What should the first thread do, and what should the second thread do? In general, we have two options. In option 1, we can divide in this way. The first thread is working on the first pixel, the second thread working on the second pixel, and so on. Then, in the next iteration, we move forward. The first thread works on the fifth element, and the second thread works on the sixth element. So we shift by the grid size. Another option is more traditional. So we partition the whole workload into groups, and we let each thread to work on its own partitions. So you can see the difference between these two designs. Of course, here we show an oversimplified scenario where there are only 4 threads. In a GPU implementation, there should be thousands to tens of thousands threads, but the mechanism stays the same. So which one is the better option? For CPU, you may say option 2, because it's straightforward and there's no performance difference. But for GPUs, in general, option 1 is better for GPUs. So this is because memory coalescing. If two adjacent threads are accessing adjacent data, the memory access of these two threads can be coalesced and to make it in one thread. In this case, we can save a lot of memory traffic, which we will focus on talking about in the next section. In this case, we're discarding option 2 and let's implement option 1. So we fill this gap by introducing these incremental steps, which is the global size. That is the total number of threads within the grid. So after implementing this kernel, we also need to make slight modifications to the host program, which I won't show in these slides. Previously, we set the grid size to be the number of pixels in the image. In this time, we should change the grid size and the block size. As previously discussed, we say 64, 128, 256 are good values for block size, so we use 256 in this time. Then for the total number of threads, or the total number of blocks in this grid, it's a variable that we can decide. Basically, we can set it to any number we want. We can set it to a really small amount of threads, so each thread will do more work, where we can have a lot of threads, so each thread will do a small amount of work. So how we can find a good balance? So what is the performance? Remember this figure, the performance stops at about 60 milliseconds. If we introduce these fixed size kernels, what we can do? Let's compare this execution result with the fixed size kernel. So let's still try to profile the performance of this application. So this is the previous performance line as we change the block size. And this time we keep the block size to be 256 and we change the grid size. As we change the grid size, which equals to the number of blocks, we're actually changing the total number of threads that are available in the whole GPU. So first thing you may notice is that the bottom of this curve is actually much lower than the curve on the left. This shows the power of reduce the number of threads because the dispatching pressure is much lower and each wavefront can live longer in the compute unit. And we can almost double the performance by making this minor change. And then we can see this curve. When we only have a small number of blocks, our performance is still bad. That is because, remember, when we talk about GPU architecture, one block can only execute in one compute unit. And we have 60 compute units in MI50. If we only have one block, we can only use one wavefront. If we only have one block, we can only utilize one compute unit. So if we increase the number of blocks, we will improve the performance as we can utilize more compute units and we can utilize more memory bandwidth. And then you can see there are still some sort of jigsaw pattern. The first low point happens around 60. That is because the MI50 has 60 CUs. As we increase the number of blocks to a higher value, we actually have another round of blocks that are being scheduled on these 60 CUs. And as we keep increasing the amount of blocks, our performance keeps decreasing. At about 300 blocks to 600 blocks, our performance becomes stable. We can pretty much fill the whole GPU and utilize all the computing power and the memory bandwidth of that GPU. So as a summary, we can say this grid size fixed kernel can significantly improve the performance, but can be a little bit harder to code.